Grade 12 Functions, Section 1.5. Today we're going to be discussing inverse relations. So, first of all, let's start with an example. Recall that the volume of a sphere is given by the relationship V is equal to 4 over 3 pi r cubed. Determine the equation of the inverse. Okay, so basically what we're doing here is we're expressing V in terms of r. Okay, so the first thing we're going to do is look for where our V is, where our r is, perfect, have it highlighted, and we're going to get rid of the denominator. So here we're multiplying everything by 3, getting rid of the denominator that way, and now we're left with 3V is equal to 4 pi r cubed. Now we're going to get rid of the 4 pi r, and we're isolating for r cubed, basically. So once we divide everything by 4 pi out, then we're left with 3v over 4 pi is equal to r cubed. And then now, once we have that, they skipped a step here, but we're going to now get rid of the cube root. So in this case, we're cube rooting both sides, and once you do that, you're left with r is equal to the cube root of 3v divided by 4 pi. So now we have a question here, which is the inverse of a function always a function? And the answer is no. So as we've seen previously, we can have y is equal to x squared and y is equal to square root of x. And we can use the vertical line test to tell us whether each x is mapping to its own y. And in this case, we can see that when we have y is equal to x squared, that holds true, that passes the vertical line test. When we have y is equal to square root of x, it does not hold true, and we need to restrict our domain in order to make the function a function and not a relation. So this tells us the importance of domain and range, and in order to find the inverse function, the first thing we need to do is switch our x and y, which is what we did here. So by switching our x and y, we're basically switching our independent variables. Okay, so here's an example. Given f of x is equal to x squared, find the inverse relation, then compare the domain and range of the function and its inverse, and lastly, determine if the inverse relation is also a function. Okay, so here we have part A, we have y is equal to x squared. First thing we do is switch our x and y. Then we get y is equal to x squared, so we switch it. We get y squared is equal to x, and then y is equal to plus minus square root of x. For part B, we're comparing the domain and range. So f of x, we have the domain being x is element of the reals, and r being y is equal to domain of the reals as well. And then for the inverse, we can see that if we make the domain and range both x and y element of the reals, it doesn't hold true, right? Because then we no longer have a function, we only have a relation. So as a result, we see that there's a restriction needed. So we can either have positive or negative x's, but not both. Perfect. Okay, and so for part C, we then know that it's not a function unless the domain is defined. So here's a summary. It tells some important things about inverse functions. So the inverse function of f of x is denoted by f inverse of x. So when we have f to the power of minus 1, it looks like it's to the power of negative 1. That's what the notation is for an inverse function. And function notation can only be used for the inverse of a function. So the graph of the inverse function is a reflection in the line y is equal to x. So this is really important. So if you look at, let's say, this function, even this example right here, this line y is equal to x, that is actually giving us a reflection of the original graph and the inverse of that original graph. And we see that holds true here as well with our y is equal to x squared, right? This line y is equal to x is there again, and that's the line that tells us that there's actually a reflection happening between our original and our inverse functions. Okay, so then we need to know that not all inverse relations are functions, as we found in that example, and that the domain and range of the original function may need to be restricted to ensure that the inverse of the function is also a function. In order to find the inverse algebraically, write out the function equation using y instead of f of x, then exchange x and y, and then solve for y. And then also, if a comma b represents a point on the graph of f of x, then b comma a represents a point on the graph of the corresponding inverse. So given a table of values or given the graph, you can switch the x and y's accordingly to give you the graph, give you information for the table of values and for the graph of the inverse. And lastly, the domain of the function is the range of its inverse, and the range of a function is the domain of its inverse. Okay, so then here's some examples. So Each of the following ordered pairs is a point on a function. State the corresponding point on the inverse relation. So it's pretty straightforward. We're just switching the x and y's. So for A, we have 2, 5. That switches to 5, 2. And then for F, you might be a little bit confused in the notation, but remember, h of 0, that just means y. So we're saying that y is equal to 7, and the 0 is the x you're putting in. So that means that your ordered pair would be 0, 7. So then when you reverse it to find the inverse, you get 7, 0. Okay, question 2. Given the domain and range of a function, state the domain and range of the inverse relation. So for part A, we have f inverse of x, and we see the domain that is given is x element of the reals, and r is y element of the reals, so therefore once you switch it, we also get reals for both. And by reals, I mean real numbers, I should say. Real numbers for both. And then for D, we have, in the original, we have domain is x element of the reals, and x is such that x is less than -2. And for range, we have y element of the reals such that y is greater than -5 and less than 10. So therefore, once we get our inverse, the domain and ranges are going to switch, right? So therefore, we know that our range then becomes y's element of the reals such that y is less than -2, and the domain becomes x's element of the reals such that x is between -5 and 10. Okay, so let me match the inverse relations to their corresponding functions. So A matches to D. And how do you know this? Well, if I were to actually draw our line for y is equal to x through this function, draw that same line through here, we can see that then these functions are actually reflected across the y equals x line. So that's how we know graphically, which function is an inverse of each other. So you follow that same process through, then you can see that B and F are inverses, and C and E are inverses. Okay. Then we have determine the inverse of each function. So for example, we have y is equal to 3x plus 4. So it's x and y, and then we're isolating for the y. So pretty straightforward. Then we have -3y is equal to -x plus 4. Therefore, 3y is equal to x minus 4. And finally, we have the inverse function is equal to x minus 4 over 3. So it's important here notation-wise to give the answer in the notation you were given, right? So in this case, we were given our question in function notation, so we're going to return the answer in function notation. Even though we switched to this notation in between while solving, we're going to return it in this notation, the function notation we were given in. Question C, g of x is equal to x cubed minus 1. So first we put in terms of y, then switch the x and y. Then isolate for the y and solve for it, and then we finally get our function, our inverse function again. Okay, and that's all for this video. So I hope to explain a little bit about inverse functions, and I hope it clarified some things for you. As always, if you have any questions, feel free to contact our tutors on our website, go on the forum, and don't forget to like, comment, and subscribe. Thank you.